Started. And all right. So I got the exam graded for this class in record time. Okay, as far as I'm concerned, that's record time within a week or so. Um, and the grade distribution, I got it plotted too. This is also kind of for the first time, in teaching many of my classes. This is the plot of the score for this class. 100% is actually 100%. Okay, so that is not just points. So 100 is just 100%. So you can see that about two people got like A's based on the grade um, assignment scheme of this class. A third person got pretty close, but not quite to 87.5%, but pretty close. And then basically from here all the way to 62.5%, which is this here. So all of these people are getting B's in this class. And then from here to 37.5%, which is about here or here, like I cannot tell which one. Those are all getting C's in this class. And then from here to here, from to 12.5%, these are D's. And then one person on this chart, or actually a few people on this chart, are getting F's in this particular exam. So that's kind of the distribution of the grades for this class at this point. No, just one. This is just for exam 2. So I have to do another plot for exam 1 if that is what you want. Yeah, but this is just for exam 2. And if you kind of flatten out the curve, it is kind of bell curve. It looks like a bell curve. So are there any questions about the distribution of scores or any other comments about the test? No, no particular questions. Mm-hmm. Yeah, absolutely. Yep, I have photocopies of the test. So if you want your paper copy back, that is certainly something that I want to do because I don't have to keep your physical copy. I just didn't bring it today because I have to restaple everything and then bring it back. And if you have any questions about the scoring of a particular question, feel free to come to my office and I can explain, how I did the scoring, and if I made a mistake, I can, correct that as well. Okay, is that good? All right. All right, so we're getting back to our merge sort, okay? Do you guys still remember the merge sort example that we did before the break? What merge sort, right? before the break. So we did an example of merge sort. I did not keep the file, so I don't have a copy of that. But if you watch the video of the lecture right before the break, that would have the yeah. So that would have an example of merge sort. Since you are also taking 430 or have taken 430 already, did they talk about the merge sort algorithm in 430? They did? There. Okay. Sorry? Right. So the one that they talk about in that class is for using an array, and they keep it keeps chopping it down to half the size, right? Instead of working with runs. So that algorithm would not work very well when you're using tapes, because it keeps breaking things down recursively into until they get down to 2. Then you can get the 2's sorted. Then you can merge the 2's and the 2's to the 4's, and then the 4's and the 4's to the 8's, and so on. The one that I used in, let's see. So the one that I use in module 0079, that one is basically super friendly to mainframe computers who which used tapes, because tapes are not random access devices. They are very good at sequential access. The bandwidth of sequential access is really good, but they are not very good for random access. If you want to do things in RAM, this one can do it too. So basically, the comment that you have is, this one is different from the one that you guys talked about in 430, and that is true. Okay. But it doesn't change the time complexity, which is the focus of today's lecture, or at least the first part of today's lecture. So when we look at the time complexity of merge sort, whether it's recursive or not, it is T of n, which is the actual time it takes for a merge sort implementation to solve a problem, where n is the size of the array or the number of items that you need to sort. It's an element of big theta of n log n. What that means, okay, if you guys remember, there are a few symbols that are really important. There's big O, and what does big O represent? The upper bound, very good. So just because it is an upper bound doesn't mean it is a tight bound, which means it can be a gross overestimate of the actual time that it takes, okay? What about big omega? And that's the lower bound, okay? But the lower bound can also be a gross underestimate of how much time it actually takes. So if you use a gross overestimate and a gross underestimate, it's not really telling you a whole lot, right? Because it's just telling you, oh, it's not exponential and it's not constant time. But there's a lot of stuff in between, okay? So if you want to get more information, you want to get to big theta, which is a tight bound. This is where the same estimate is both a upper bound and also a lower bound. Then you have a tight bound. So big theta is good. If you can actually get to big theta, it is really good because now you can say, oh, okay, so we do not just know the upper bound or the lower bound, we know exactly what the curve should look like. So in this case, we do know it is big theta of n log n. So that means the amount of time for merge sort to execute based on the length or the number of items you have to sort is n times the log of n. Now the base of the log is not specified because it doesn't matter. Okay, because base 2, base 10, base e, all you're really changing is a constant. And the constant is useless in the discussion of time complexity. So are we doing okay so far with these terms? So we're remembering, vaguely, the discussion of the time complexity, upper bound, lower bound. Okay. So now we want to talk about a proof of, why it is n log n. There are two proofs here. One is formal and one is informal. So we'll skip the informal one and go get to the one that is formal. So the basis of the proof is we want to basically look at algorithms where the time complexity is slightly recursive. So the time complexity to solve a case of n equals to k1, which is just a constant. It is not based on n, has no relationship to n at all, plus k2 times n. So this term is linear to n. Okay, so k2 is just a constant that we multiply to n, plus t of Rn. So R is basically a ratio. It's between 0.5 and 1. Okay, and t of 1 minus R, the other side of n. So together, t of Rn and t of 1 minus R, the whole thing times n, takes care of the recursive calls. So there are two recursive calls, each one to take care of one portion of the original problem. But when you add up the two subproblems, they basically add up to the original problem. Is that okay? So the split doesn't have to be constant. It doesn't have to be half and half. It can be 1/3 and then 2/3. It can be 2/5 and 3/5 and so on. As long as they just add up to the whole, it's going to be okay. Is that okay? All right. So if we have Tn defined this way and it is recursive in a way, so the question is, how do we know that this is going to give us a tight bound of n log n? That is the question. So the way we do this with the formal proof is, I think the best way to do this is to show you a picture. Okay, so let me show you a picture that you have seen already. Okay, so let me start up. I think it's under accessories. Yep, there we go. All right. So the best way to look at this is you have a size, an original size of n, and the algorithm splits it into two portions. The two portions do not have to be identical. Once it can be lopsided. So you have r times n going to one side, and then you have 1 minus r, the whole thing times n going to the other side. Is that okay? So let's say your original problem has 10 items, n equals to 10, and then r is 0.7, okay? So you have seven items going to the top branch, and then you have 3 items going to the bottom part. Is that okay? And then we split again, right? So the top one splits again, and the bottom one splits again, using the same ratio. Now, it doesn't really have to be the same ratio. I'm just using the same ratio just so that it's easier to prove, later on. So we have, this is now becoming r squared n, and this is r1 minus rn. And then the bottom one here, we have 1 minus r times rn, and then we have 1 minus r squared times n. Is that okay? So I'm always using the top branch for the ratio of r, and the bottom branch to be the ratio of 1 minus r. Is that okay? What if I split again? Well, it's not going to be very exciting. If we split again, we have r cubed n, and then we have r squared 1 minus rn, and then this is r squared 1 minus rn, and then this one is r1 minus r squared n, and then this one is 1 minus r squared n, and then this one is 1 minus r itself squared rn, and then this one is 1 minus r squared rn, and then this one is 1 minus r cubed n. Is that okay? So are we kind of understanding the general approach? Because I don't want to draw another layer of the branches, okay? Because it's exponential in terms of the number of nodes, but you guys get the idea, right? Haven't we seen something like this before? Probability. Binomial distribution. So when you look at this, it is really binomial distribution. Forget about n, okay? Because n appears in every single one of these expressions, so you can just take it out, okay? So once you take out n, what do you get? You basically get 1 here, right? Because n is 1n, and if we divide everything by n, that 1n becomes just 1. So then we have r squared, we have r here, and then we have 1 minus r, and then we have r squared, r times 1 minus r, and so on. So what we are ending up with here is a binomial distribution, okay? Because if you look at r cubed, we only got one of those, okay? We only got one of r cubed. When you look at 1 minus r cubed, we also only got one of those. What about r squared 1 minus r? We got one here, okay? And then we got another one down, let's see. We want r squared, right? So there's another one here. And then we also got one here. There should be one more. Is there another r squared? Nope. Okay, so we got 3 of those. So I'll just put a special symbol here. And then what about 1 minus r squared times r? We got 3 of those too. So we got 1 here. I'll use a double circle here. 1 here, and also 1 here. 1, 3, 3, 1. That's the ratio that we are getting, that we are looking at. But that's also, remember Pascal's triangle? 1, 1, 2, oops, okay, take it back. 1, 1, and then 1, 3, 3, 1. Remember Pascal's triangle? Because Pascal's triangle gives you the combinations. Okay, so in order to have 1r and 2 of 1 minus r squared, we have 3 of those. So we're getting back to the basics, right? But now the question is, how many n's are we talking about? Remember, n is divided out because it doesn't really matter. So we are really just looking at, if I add up all of the nodes of the same level, what should I be getting? And every single time we're getting 1. Okay? Now, what do I mean by that? So if you just add up, r squared, r cubed, okay, plus r squared times 1 minus r, and we know there are 3 of these, right? So times this by 3, plus r times 1 minus r, the whole thing squared, and we know there are 3 of those, and then plus 1 minus r and to the whole thing to the cubed, and we just want to add up all of these terms. What do we get? We get 1. So that means we have 1 n here, we have 1 n here, we have 1 n here, and we also have 1 n here. Is that okay? Are we still doing okay so far? All right. So when we plug all of these numbers back into the equation that we talked about earlier, so when we plug all of these back in, then we have to plug it back into this equation here. The only term, so K1 is unique, okay? So we have to multiply K1 by the number of levels that we get. Actually, by the number of nodes that we have, okay? So that one is proportional to n, so we have n of K1. What about K2? How many of K2s do we have? Each level has n items, right? And then everything is proportional to n. K2 is proportional to n. So we just have n squared. No, it wouldn't be n squared, because if you break down all the nodes for each level, each node only has, and the sum of all of those is n. So we only have K2 times n also. Is that okay? Yes? And then these terms here being recursive, but we know that no matter how much we add, each level is only giving us n items, exactly n items. So that's how we can come up with the time complexity of n times log n. So when you get down to here, we're getting back to the binomial distribution. This is where we talk about the binomial distribution. And this is where we talk about how the summation of all of those terms is really just 1. And because of that, now we get back to the equation of we just have n log n as the time complexity. So are we okay with this proof? Just generally the concept. I think the graph is going to be very helpful. So if you have not written down the graph or have not copied the graph, you can do it later on, because everything is getting recorded. But the graph really shows you how it looks like. And if you want to plug in actual numbers, it helps too. Just make r 0.5, okay, because that's easy to work with, and then start n with like 64. So at the top level, you got 64. So then you look at the equation. So it really helps to plug in actual number to the equation just to visualize what it looks like. So for each invocation, you have a constant K1, okay, that's per invocation. And then at the top level, because n is 64, so you have 64 of K2. Is that okay? Then you look at the second levels. The second level is split evenly. So we got 32 going one way and 32 going the other way, right? For each of those 32, we have K1, and then we have 32 times K2, and then the other one also has 32 times K2. So at the second level, we have 2 K1s, because we have 2 invocations at the second level. But when you look at K2, we also have just 64 of them, because there are exactly 64 items to process at the second level. And then each one requires K2 time to process it. Is that okay? So K1, if you add up everything, it is, when you look at the entire time complexity function, K1, the total number of K1 is going to be the number of invocations, which is going to be proportional to n. And then when you look at all the summations of K2, that's also just going to be proportional to n. But you have to multiply it by the number of levels. So now the question is, how many levels do we end up with? The total number of levels that we end up with has to do with how we split. And because in the easiest case where r is 0.5, you can now see that, oh, okay, so we basically keep splitting until Rn becomes 0 or 1, then we can stop the recursion. But how many times do you need to divide a number by 2 until it gets down to less than 1? It would be it will be log n divided by log 2. That's the number of times you have to divide it. But division by log 2 is useless because it is division by a constant. So now you just basically get log n back. But what if r is not 2? Well, it would be 1 over log r, right? As long as r is less than 1, it will still have the log effect. So is that okay so far? Okay. So with this done, we are officially done with time complexity, especially seen from the perspective of recursive algorithms. So are there any questions you guys want to ask about this module before we go any further? So we are basically done with the last module, which is a big O, big omega, and big theta notations. And what we looked at just today is from the last portion of it. No questions? Yep.
Just one thing that I don't know if I was understanding or not. Are we going to be calculating things like a big theta notation if we're given like a function or something?
The truth is, in previous years, I usually do not ask questions about big O notation because, to prove an algorithm having a certain, time complexity is a little bit beyond this class. I think it's a little bit beyond this class. That's typically the upper division algorithm analysis class at a 4-year university to derive it. So in this class, I just want to give you guys the exposure and also the understanding of, now that we have a proof, do we understand why, let's say Mergesort is n log n. So that basically is the bottom line for this class. Is that okay? All right. So with this out of the way, we are going back a little bit because we skipped graph as a topic. So we're going back to graph, which is here. Okay, there we go. And I got it opened up already. Nope, here. So now we're going to talk about graphs. And with graphs, I can ask questions, much better than I can ask questions about time complexity. Because with graphs, we got algorithms. And with algorithms, you can track, you can trace. So I can test, can you guys, track the A star or the Dijkstra's algorithm? So I give you a graph, I give you all the vertices, I give you all the edges, and you guys have to show me, okay, I know how to find the shortest path because I can follow this algorithm. Okay, so that's going to be the focus of the final exam. The final exam is going to have a lot of focus on graphs, especially one of these two algorithms. So what we'll do is we'll first start to talk about what a graph is from the perspective of this class. Yes? The final what? It is not intentionally cumulative. In other words, I may, in other words, it's unintentionally cumulative. So it was, huh? Exactly, because the representation of a graph relies on the concept of set concepts, set operations, Cartesian products, element of, and so on and so forth. So I cannot, completely isolate what we had to talk about from the final exam. So you will still need to understand those concepts where, graph theories, rely on. Okay, so that's what I meant when I said, not intentionally cumulative. All right, so with a graph, the way we represent a graph is it is a two tuple, which basically all it says is it has two components, okay? It has two components. The first component, which I typically use V to represent, is the set of all the vertices, and then the second one would be the set of all the edges. So V is a set, E is a set, okay? And G, a graph, is a two tuple of these two because I don't want to mix up my vertices with my nodes. Okay, vertices is one thing, and edges are other things. I don't want to mix up my vertices and my edges, not nodes. Nodes and vertices are the same thing. Okay, so what about, so V can be anything. Okay, so when you look at V, which is a set of vertices, each vertex can represent just about anything you want. Okay, it can represent an actual physical location, like in the case of GPS. Okay, every single point, at least every intersection, in a city can be seen as a vertex. Okay, what about an edge then? Well, although you can use anything to represent, V can, each element of V can represent just about anything. The same cannot be said about E. E itself, or the set of all the edges, has to be a subset. Doesn't have to be proper, okay, but it has to be a subset of the Cartesian product of V and V. Because what it is representing is, can I go from this vertex to that vertex? If it is in this set, then yes. If it is not in this set, then the answer is no, we do not have a direct edge from here to there. Is that okay? So once again, it's good to kind of give you a picture, okay? So I'm going to use the same piece of quote-unquote paper here. So I'll give you a picture, okay, because the picture is easy to look at. So I just look at, this is vertex A, vertex B, vertex C, vertex D. Okay, I'll just have 4 vertices in this case. And then the edges are easy to draw because edges can be seen as an arrow. Okay, so I can have like edges kind of like that. Okay, and it is okay to have something like this too, because what we'll be doing in this class is we'll be using directed graphs or directed edges all the time. So everything is directional. So in this case, A can go to B, but B cannot get back to A. Is that okay? That's what the arrow is indicating. It is a one-way street from A to B, but B cannot get back to A, at least not directly. But in this case, definitely there's no path to go back. So to represent something like this, which is kind of graphical, the way we do it is we say that V, which is a set, in this case it has got A, B, C, and D, right? So that's kind of easy because the vertices are also known as nodes. So those are basically the points in a graphical representation of a graph. And then E is a two tuple. Each element of E is a two tuple to indicate the arrows. So the first arrow that I can represent is AB. Okay, so AB is a two tuple to represent the edge, that arrow that goes from vertex A to vertex B. Is that okay? Okay, does everybody understand the text representation of just an arrow in a graph? Okay. So now we can look at BC, right? BC is another edge. We have another edge AC, and then we have 2 additional edges. There's one going from B to D, and then there's one from D back to B. Okay, so that's basically E. E is a set of 2 tuples where each 2 tuple is representing an arc, an arrow, or a direct connection between one vertex and another vertex. So are we good so far? Does this remind you of relations? So E looks like a relation because it is also a subset of the Cartesian product of V over V. So are we good so far with these concepts? What is a vertex? What is an edge? What is a graph? So in this case, if I name this graph as G, then G is the two tuple of V and E. The notation is kind of important because this is sometimes how I ask questions in the test. It's like, okay, consider G1, okay, which is consisting of V and an E, and then look at G2, which can have the same vertices but a different set of edges. So it's kind of important to understand how a graph is represented. Okay. So if you want to work with graphs that are undirected, which means an edge is bidirectional, you can kind of always coerce a directed graph, also known as a digraph, so that every time you have AB in the edge in the set of edges, it automatically has BA in the set of edges as well. So it's just kind of cumbersome to represent it, but a digraph or a directed graph can represent a graph where direction does not matter. But in this class, we focus on digraphs or directed graphs. So digraphs and directed graphs are basically the same thing. One is just a shorthand version of the other. So are we good to go at this point? Terms are okay. All right. So we have some further terms to define until we get to the algorithm. A path is defined as a tuple of vertices. So in this case, edges from E must lead from vertex to the next. In other words, okay, so let's take a look at this one here. It says that I has to be an element of N, and it says here that I has to be less than bar P bar minus 1. So P is the path that is in question. Okay, P is a path. So P is a tuple of vertices. So if I is less than bar B bar P bar minus 1, which means that I is a valid index into the path, then the following has to be true. P bracket I, which is the I, which is element I in the tuple P, and then we have a comma, P bracket I plus 1, which is element I plus 1 in the tuple P, and then these two are in parentheses, so this is representing an edge. That edge has to be in E. Okay, so this is kind of abstract. It's easy to look at examples. So when we go back to here, we can now say, I can give you a path. So P can be A, B, and D. So that is okay. This P is a path because I can find an edge from A to B. I can also find an edge from B to D. So it is a path. Let me show you something that is not a path. Okay, so this is a path. So let's show something that is not a path. So let's say Q is A, D. Okay, this is not a path. Now AD is not a path because there's no edge going from A to D. But can we go from A to D using more than one edges? The answer is yes. Okay, but the path has to be done in a way so that between any two adjacent vertices in the path, there has to be an edge. And that's why AD is not a path. Even though we can go from A to D, we need to go through two edges, right? But there's no single edge bringing us from A to D. So is that okay? Now, technically speaking, a path has other connotations too, but for what we are talking about, it is not that important, okay? So getting back here, now we get into Dijkstra's algorithm. Oh, almost there. We need another function. So d is a distance function. So a distance function uses e, which is the set of all the edges, as our domain, and it maps the edges to r star, which is basically all the non-negative real numbers, as our codomain. So if you give me any edge in a graph, I can use d to say, oh, this is going to have a distance of x amount. But that x amount cannot be negative. Can be 0, but it cannot be negative. Is that okay? So what do you think is an application of a graph like this? What can it represent? Let me give you an example. Huh? Okay, so the easiest one that you can look at is look at Google Maps. And we'll look at a local portion. Okay, this is our campus map. So you can look at this map here, and you can say that every intersection of these paths is a vertex. And then all the paths going from one vertex to another, directly to another vertex, is an edge. What about D? Well, D is representing the actual distance or the amount of time it takes to go from one vertex to the other vertex of the same edge. Is that okay? So a graph can represent a map with the D function to represent distance. Is that okay? Then you will say, well, but that means digraphs are pretty useless, right? Because the amount of time for me to go from here to here and from here back to there is about the same. Why do we need to use digraphs instead? Well, to understand that, even in the context of a map, all I need to do is to go to San Francisco. San Francisco. And we'll look at the downtown area of Sacramento. That's a good way to do it. See all these arrows? What do they represent? They're one-way streets, right? So when you have one-way streets in a map, then digraphs make sense, because from here, which is the intersections of Ellis and Hyde, you cannot get back to O'Farrell and Hyde going backward like that. Now, saying it is not possible is not really absolute. It would just cost you a lot. So look at the D function as the cost, right? In terms of money, in terms of dollar amount. So that would include like fuel, it would include insurance, and in this case, it will also include the cost of collision repair, and the ticket, and the increase of insurance. So it's a cost, okay? It's not like, it's infinite. It's just a lot higher than the other way around. Is that okay? Are we good so far with, why we like digraphs more than just regular, undirected graphs? Okay? So if this is what we are looking at, okay, the contrast is not too good, on this, projector here. So if in each intersection, okay, here, 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 and so on, if each intersection is represented by a vertex, and every edge is representing, how do we get from one intersection to an adjacent intersection, and then the D function is telling us how much it costs to go from one intersection to another intersection. What do you think is some of the problems that we might want to solve using this kind of representation? What kind of question do you think people would ask when they are presented a map? Okay. Exactly. And do you want to add to it? About the same? Okay. So one really common question is, how do I get from one place to another place? Okay. So let's go ahead and play with San Francisco a little bit here. Okay. And we can just click here. Huh? Go to what? I can't see it.
In the southwest.
Southwest.
Right by your cursor.
Say again?
It's right by your cursor.
Right by my cursor. Oh, Boozland. I see. Well, it's got a lot of good rating, and not too expensive either. So you can kind of imagine if you want to go from one place to another place.
Go from the children's playground to the booze land.
There we go.
Where's children's playground?
It's a top middle. Green.
I mean here?
Yes, from there to booze
Oh, that's
land.
pretty far in the scale is of San Francisco. That is really far.
Well, we really want to go to booze land.
Well, that's the reason why people want to go to Boozland. And you can see how the children's playground has a not so good rating. I mean, it's only 3.5 stars, while Boozland is has like Boozland has got 4.5 stars. That tells you why we have a population decline. So yes, but the answer is yes. Okay, one common application of a graph is show me the shortest path from here to there. Okay, find a path from here to there. Okay. So before we move on to Dijkstra's algorithm, I'll give you another map to set up the context. Okay, so I'll go to Six Flags, and hopefully it has a map of what is inside the amusement park. Yeah, it has some, but I know, but I want to make sure that we have a map that is detailed enough. That's actually not bad. That's actually pretty good. So you can use Google Map to navigate inside Six Flags. That is cool. I mean, if you turn on the location tracking part of, the kid, with a cell phone, you can locate and actually, ask, how to get to that person quickly. The reason why I want to set this up as a context, zoom in just a little, there we go. Okay, so the reason why I want to mention this is, imagine you're going with a particular kid, okay? And, as they always do, okay, they want to look for a bathroom, okay? And now you have certain locations that are bathrooms. And you say, find me the closest bathroom, or the bathroom that would take me the least amount of time to get to. That would be a common problem, right? So you do have multiple bathrooms, but you want to get to the closest one. Make sense? Unless the kid says, no, but I want to go to that one. A specific one. Okay, so now how do we solve that problem? Because we are not having a particular definite destination. We have a set of alternative destinations, and we want to find the shortest path to the one that is the closest to us. Okay? But we don't want to, find the shortest path from my current location to one bathroom to another bathroom to another bathroom to another bathroom. Do the comparison and then find the one that is shortest to me. I want to solve this problem like in one shot. Okay? That turns out to be Dijkstra's algorithm, but not the way it is presented in 430. So the way Dijkstra's algorithm is presented in 430 can only find the shortest path to one particular destination. But the way that I modify that algorithm for this class will find us the shortest path to the closest vertex that is classified as a destination. So from that perspective, it is a little bit different from the one that you learned in 430. So just kind of keep that in mind. So let's go to the algorithm. So this is Dijkstra's algorithm, and we start with a description of the symbols, okay? And without any big surprise, the graph is represented as G, which is a tuple of V and E, okay? V, once again, is the set of all the vertices, and then E is the set of all the edges. Are we good so far? I mean, this is consistent with the use of symbols described earlier. And then we have a d function, the distance function. And it is described exactly the same way as before. It is a function that will map an edge to the distance of that particular edge. Now, distance is really in quotes. It doesn't actually have to be physical distance. It's basically just the cost of traversing a particular edge. So just remember, d is not always necessarily actual distance. And then we have a subset of v, which is the subset of vertices that are identified as our destinations. Is that okay? So it kind of makes sense that we have at least one vertex in this particular set, but we can have more than one. Okay, you can have 5 out of 20 vertices being classified as destinations in this case. So are we good with these with the terms? Okay, so this is the problem that is given to us. So the first 2 lines basically just sets up the problem. What is given to us is described by these 2 lines, and then the rest of it would belong to the algorithm. So this line here says for each v in the set of destinations, we want to initialize L of v to be 0. So L of v is basically representing what is the length of the shortest path to get to, what is the length of the shortest path from vertex v, lowercase v here, to a destination. Does that make sense that we do this kind of initialization? And why does it make sense? Why do we initialize all of these v to have a L value of 0? Where did I get these vertices? I'm getting these vertices from a subset, but there's something special about that subset, right? What is this subset? They're the destinations. Would you agree that if you're standing on a destination, the length of the shortest path to a destination is going to be 0 because you are on it? Yes? Okay, well, that's why we initialize the L value to 0 for every vertex that is itself a destination. Is that okay? So moving on to onto the next line. So the next line is initializing everything else. So let me highlight it first, then we'll talk about it. Okay. So this is initializing everything else, all of the other vertices. So it is for each vertex lowercase v that is not a destination. It is a vertex, but it's not a destination. Remember the use of the subtraction symbol in when we talk about set operations? Yes? Okay. So we're excluding all the destinations. Anything that is not a destination has an L value initialized to infinity, because we haven't explored yet. Okay, so if we have not explored yet, then we make the assumption of nope, it's not reachable unless I can prove that it is reachable by an edge. Is that okay? Then the next one is initializing the set of boundary vertices. So in this particular algorithm, the set Q is going to change over time. You can kind of look at elements in Q as, well, we just updated the L value of that particular vertex. It might propagate some changes to vertices that can go to that particular vertex. So we might need to do some updates. Let's check it. Okay, so that's what Q is representing. Q is representing a set of vertices where it might propagate changes to other vertices. So we should take a closer look at those vertices. So it is initialized to what? It's initialized to the set of all the destinations. Because guess what? Those are the ones who got initialized with a value of 0 to begin with. So maybe that, okay, might trigger some changes to other vertices that has edges going into a destination. So that's why we initialize Q, the set Q, to the set S. The next line initializes E prime to be an empty set. This is the set of what I call solution edges. In other words, if you want to, at the end of this entire algorithm, E prime is going to contain the edges representing components of paths to, in this case, bathrooms. Okay? So E prime is going to be constructed as we run the algorithm, but initially it is empty, okay? Because until we explore the map, we cannot do anything. Dijkstra's algorithm is in many ways easier to understand compared to A-star algorithm. One reason is, well, the while loop is pretty simple. As long as we still have vertices that might cause changes to the L value of other vertices in Q, don't stop. Keep doing stuff until Q itself is empty. Is that okay? And then we look into the while loop. The first thing in the while loop is this particular operation. It looks really awful, but it's actually very simple what it wants to do. So what we want to do is to look into Q and say, find me a vertex in Q. But wait, how do we know that there is something in Q? What do you think? Why can I be sure that there is something in Q at least? Well, the initialization is outside of the loop. Yep. Because I'm in the body, exactly, because I'm in the body of the loop, and to stay in the loop, Q cannot be empty. So I know that Q has to have at least one element, okay? But what if it has got like 20 elements, then which one should I pick? Well, this is the selection criteria. The selection criteria is for every vertex W that is also in Q, L of V has to be less than or equal to L of W. What does that mean? So what am I really saying? I mean, the rest of the sentence actually explain that, but huh? I'm trying to find the most promising vertex. Of all the vertices that are in Q, give me the one that has the shortest distance to a destination. Okay? It's a greedy algorithm. Okay? This makes it a greedy algorithm. It just says, give me the one that looks the most promising. I'll look at that one first. Okay? So now that we have selected the one single vertex V that looks the most promising, if there's a tie, just throw a dice. Okay? Pick in random if there are ties. So the next operation is we take it out of Q. So we take this vertex V out of Q. Can't we just say Q minus V? Do we really need that curly brace around the V? And why? Exactly. Yep. So there's the type requirement of you need a set on the left-hand side and also a set on the right-hand side. V itself is not a set. Okay. Now it can't. Okay. This is confusing. V itself can be a set, but it is not a set of vertices from the perspective of this particular G. Okay. So we take V out so that we are not going to reconsider V indefinitely. And then we have another loop here. This for each loop is nested within the while loop. So the syntax of this pseudocode is kind of like Python, because there are no open and closed curly braces. The indentation alone indicates what is nested into what else. So this is pseudo Python. Just the spelling itself is fun, right? P-S-E-U-D-O and then P-Y-T-H-O-N, pseudo Python. It's a fake snake. So we can use a logo like a plasticky kind of snake thing as pseudo Python. Anyway, so what do we do with this loop? We say for each E, for each edge E, in this particular set, do the following. So what set are we talking about? Okay, so let me point out which one we are talking about here. So what is so special about this particular set? We have already singled out a particular v, so w is the unbound variable. So what are we talking about here? All the vertices, all the edges that go to vertex v. Okay, so look at every single vertex, look at every single edge that is going to vertex v. Okay, so by doing this, by selecting this E, I'm also going to bind W. I'm also going to bind this W here with the next sentence. So I'm just giving the name to the vertex that is going to vertex V. So we are now looking into this particular statement here. Because the for each is only binding E to a particular edge, so if I need to name the vertex that is going to vertex V, this will give it a name. It is vertex W. Is that okay? So we are now inside the for each loop. We're looking at a particular vertex that has an edge going to vertex V. Is that okay? And what are we talking about here? What is the next statement? It is a conditional statement. And what do you think this condition is trying to do? I'm even using the colon as in the Python syntax. But what is this condition trying to say? If L of V plus D of E is less than L of W, then do the following. What is the significance of L of V plus D of E being less than L of W? First question, okay, is what is L? What is L of something? What is it representing? What is L of W representing? It's the length of the currently known shortest path to a destination from W. L of W is representing that. Is that okay? If that is the case, then what is L of V plus D of E? What is the significance of that? It is the curve, exactly, it is another, it can be potentially another path, right? Because we know that V is going to a destination using the length of L of V, okay? And we also know that W is going to V using HE, and the distance of HE is D. So these two added together is, well, this is another way for W to get to a destination. And this is the length of that path. Is that okay? Okay, so we are now looking at a particular path of W going to a destination through vertex V. But why is it important to know that this is less than the length of the currently known shortest path from W to a destination? Why is that less than important? Because now you have a new shorter path, okay? So when this condition is true, it means, oh, we just found a shorter path. Well, what do we do when we find a shorter path? Well, we want to maintain that, right? We want to remember that shorter path. So the first thing we do is to keep track of the length of the shortest path. So we basically say, LW, that we had before, that's not true anymore. Okay, that is not the actual length of the shortest path because we just found a shorter path, right? So we update that first. Is that okay? And then what do we do? This looks really ugly, but it's not really that bad. So we basically look at all the things that we have in E prime and say, if we have anything going from W to anything else, let's erase those edges in E prime. Because those edges are a part of the other quote-unquote shortest path from W to a destination. Let's get rid of those because those are not accurate anymore. We just found a shorter path. Is that okay? So the highlighted line here, or the highlighted portion, all it is doing is to say, let's erase what we knew about the shortest path from W. That's all it's saying. Okay, it's just breaking one link though. And then what we do is now to say, okay, now that those are erased, we can now add the actual edge back into the E prime. because we know that W can go through V to a destination, and that has the shortest length at this point. So that's why we want to put that into E prime. So E prime gets E prime unioned with the edge WV in a set. Are we good so far? Because I want you guys to understand the rationale of each statement, because otherwise this can be done with a whole lot less words, right? And then what do? Well, this is the part where we put something back into Q. Because if we just update the L value of W, that means things that go into W can also be changed. So that's why we are adding W into Q, so that now, in some future iterations, W will also be considered, and we'll look into things that go into W. Is that okay? So that basically is the end of the inner loop. And because the inner loop, the inner for each loop is the last thing inside the while loop, so that's the entire algorithm. The very last part, which is outside of the while loop, is just saying, oh, our solution graph is G prime. G prime has exactly the same vertices as G itself. The only thing that's different is it uses E prime instead of the original E as the edges. Is that okay? Well, let's go ahead and check it out. Now, let's make an example, and we'll track the example and find out, how the A-star algorithm actually works. So get back to Zerno. There we go. And do you guys want to start with something that's a little bit tricky or something that is not too tricky? Something simple, but not too simple? Because something that's simple is like this, and it is a destination. Well, actually, let's do that, okay? So we'll do exactly that, okay? We'll say that G is the set of vertices is just A, and then there are no edges whatsoever, okay? Because we want to make sure the algorithm can handle the simplest case like this too, right? And also, S, which is the set of all the destinations, is the same as the set of V, which is only vertex A. Is that okay? All right, so now we go to the algorithm. And, okay, this is going to be a little bit difficult to track. How should I do this? I suppose I can do it this way. I can display the algorithm on one half of the screen, and then display this stuff in the other half of the screen. But I want to see if I can zoom out a little bit. Would that still be doable, or is that too small? I can zoom in just a little bit more. Is that okay? All right, cool. Okay, so we'll go through the initialization of the algorithm, which is going to be very simple because we only got one vertex, right? So we now say L of vertex A is initialized to 0. Is that okay? And we don't have anything that is not a destination, so this part of the algorithm has nothing to do because V minus S is empty. Then we go to the next one, which basically says Q is just A itself, right? That's what the initialization of Q is going to do. And then E prime is an empty set. And then we get to the while loop. So we now get to the while loop here. Is this condition true or false? It's false. It's true. No, it is false. True. It's true. Okay. I keep confusing myself with equal and versus not equal to. Q is not empty because we just put something into Q. Q has a single element of A. So it's not empty. The condition is true. We get into the loop. We get to here, okay, even though it says blah, 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 a lot of stuff. Well, since we only got one element, we have to choose that one, right? So we choose vertex V is now vertex A, and then we scroll down a little bit in the algorithm. So now Q is empty, right? Because we have to remove that from Q. And then we have to go to the for each loop. So do we have anything to do in the for each loop? Are there any edges going into vertex A in this case? Well, it's the only vertex in the entire graph, so nothing goes into A. So the for each loop is done just like that because there's nothing to do. So we get back out into the while loop. So we get back out into the while loop and reevaluate, is Q different from an empty set? Q is the empty set. So Q is different from the empty set. It's going to be false. And then we get out of the loop. So now, when we get out of the loop, we have exactly these things here. So G prime is going to be just A and an empty edge set like that. That would be our solution. But does it make sense? Well, you're already standing on a bathroom. You don't have to go anywhere to go to the bathroom, right? Hmm?
You have to go into the bathroom.
Yeah, but that's a graph inside the vertex, right? So if you need navigational help inside the bathroom, then you have to look at another graph. So it does make sense, right? Okay. So let's look at another example then. We got time. So let's look at one where it is a little bit more tricky, okay? Just a little bit. So what we want is two paths, okay? So A goes to vertex B, it goes to vertex C, and both of those will get to vertex D, okay? Like that. But we want this to be tricky. So we want it to initially look like the vertex B is going to be on the shortest path, and then later on find out that no, it is actually an awful choice, okay? So there's a edge of a distance of 1 going from A to B, and the edge going from A to C has a distance of 20. So initially it would look very good. Yeah, let's use B, okay? And then we have another edge here which is really bad, okay, having a distance of 30 going from vertex B to vertex D, whereas the other one is not too bad, okay? Let's say a distance of 5, like so, okay? Would that be a good example? Yeah, because now we can see how the A star algorithm would actually, it knows when to switch sides, okay? All right, so this is the graph. And because I want to show you the algorithm or the trace with the graph here still being displayed, so I'm not going to be doing a lot of details, okay? So I'll just be writing all the stuff down here. So the first one, so I'm going to use a double circle to indicate this is a destination, okay? So the initialization says, L of D is 0 because it is a destination. And then the L of everything else are infinity, right? Because they are non-destinations. Does it make sense? Okay. And by definition, we also know that the set S only has one single element, which is D itself, like so. Are we good so far? Oh, actually, I take it back. No, it will still work. No, this doesn't work the way I want it because I forgot that Dijkstra's algorithm works backwards. So I'm going to have to flip something here. I'm going to put this 30 into here and then this one back here. Sorry about that. Because otherwise it won't switch side. It would latch onto the correct shortest path and just keep that one. But this will make it switch sides. Okay, so now we get to the first iteration. So Q is initialized to just as, so it initially just has one single element D, right? So now we look at the algorithm, we pick out the vertex D to be our vertex v as the variable v in the algorithm. And then we look into all the edges going to vertex d, okay? So as a part of that process, we'll find out that L of b, which is now currently infinity, is greater than L of d, which is 0, plus the distance going from vertex b to vertex d, which is 1. So as a result of that, we will do a few things, right? So the first thing we're going to do is to update the L value of b. So we now say L of b is just going to be L of d, which is 0, plus d of bd, which is 1. So it's updated to a 1. There's nothing to erase from e prime, so e prime is still, there's nothing to erase. And then we'll add the edge to e prime. So e prime is now going to be the edge bd. And then we're going to add something to q. So q, I'm going to wrap it up here. So q, so q is now, I forgot to remove q earlier. So d is supposed to be removed from q at this point, but I do have to add b back into q, okay? And that completes one iteration of the for each loop. Now we go for the second iteration of the for each loop, because after all, there are two edges going into vertex D. So now we look at the second edge, which is CD. So now we evaluate L of C, which is infinity. It is greater than L of D plus D of CD, because infinity is greater than any actual value. And as a result, we get into the conditional statement. The first thing we do is we update L of C to be 0 plus the distance from C to D, which is 5. So it's now updated to 5. And then we get through all the same stuff here, which is E prime is now, we add one more edge to it. So BD is still there, but now we also add CD to it. And then Q, we also have to add C to the set Q. So now it is BC in Q. And that would be the second iteration, the end of the second iteration of the for each loop. Then we get back to the beginning of the entire while loop, and we ask, well, is it empty? Nope, it has got two elements this time. So when Q has more than one element, then we have to ask, well, which one should we pick? Remember, it is a greedy algorithm, which means it will pick the most promising vertex out of Q. So we look at these two, okay? L of C is 5, which means the length of the shortest path from C to a destination is 5 at this point. But L of B is only 1, which means the length of the shortest path from B to a destination is only 1. I'm going to pick B because B looks more promising. So now we say Q is only C because we remove B first. V is B. And then we look into the vertices or edges going from something else into B. And there's only one edge here, which is AB. So now we evaluate, okay, so this goes around here. So we now look at the L of A. L of A at this point is still infinity. And it is, in fact, greater than L of B plus the distance of going from A to B, which is 30, right? So now we update L of A and say, you're not infinity anymore, you're now 31. Because we found out that it takes a distance of 1 from B to a destination, but to go from A to B is 30. So we now know there is at least a path of 31, of length 31, going from A to a destination. So we update it. So once we update that, we have to go back and update a few other things. So we have to update E prime and say that, okay, we got BD, we got CD, and now we also have AB in it. And we have to add it to Q. So Q is now AC, okay? And we're done with the inner loop, the for each loop. We go back to the outer loop, which is the while loop. So the while loop says, okay, is Q empty yet? Because if Q is empty, I can go. Nope, Q is not empty. Q has got two elements. So now I have to use the greedy algorithm again and say, which one looks more promising? Which one has the lower L value? C has an L value of 5. A has an L value of 31. So looks like C is going to be the one that I pick. So now we say Q is just A because we take C out of the set. And then we say V is C. So now we have to look into all the edges going to vertex C. How many edges go to vertex C? Just that one here, okay? So now we reevaluate L of A. So we now ask the question again, look at L of A, and we ask, is it greater than, okay, this is a question mark, is it greater than L of C plus the distance of going from A to C? That's a question. What do you think? It is yes, okay, because L of C is 5, okay? The distance of going from A to C is 20. 20 plus that 5 is 25. 25 is less than 31. So the condition is true. So we go into the then portion of the conditional statement, and we got a few things to do. We have to update A again. So this time we update it to 25 from 31. But this time, this operation actually has got something to do. Because in E prime, do we have anything going out of vertex A in E prime? Yep, we got AB, so E prime has to be updated now. So E prime is now updated to just BD and CD because we removed the last one. Anything going out of A is going to be removed from E prime. But we're going to add it back. Okay, we're going to add back, so we got BD, CD, but we're going to add back AC at this point. Okay? And then what else do we need to do? Q. Technically, we are adding A to Q, but since Q only has A at this point, so it doesn't look like we are updating it. But technically speaking, we are adding vertex A back into Q, except it's already there. Is that okay? So we are now done with the inner loop. We go back out to the while loop. The while loop says, well, I cannot quit until Q is empty, and Q is not empty. It's got a single element now. Well, let's take it out. So V equals A, Q is empty. And now we need to look at all the edges that go to vertex A. Do we have any edges going to vertex A? Nope. So that means the for each loop has nothing to do, and Q is now empty. We go back to the outer loop and we ask that question again. Is Q empty? Yep, it is empty. Time to quit. So what we end up with here is E prime being BD, CD, and AC. So I'm going to pick a different color to highlight here what edges remain in the set of E prime. So we have BD, okay. BD is still here. CD is still here. And then we have AC here. Okay? So the red edges are representing the solution of applying Dijkstra's algorithm. So you look at this and go like, what is that representing? Well, the cool thing about this version of Dijkstra's algorithm is it finds the shortest path from every vertex to a destination. It doesn't just find a shortest path from one vertex to another vertex. It finds the shortest path from every vertex to a destination. So with this in hand, now it doesn't matter where that little kid is going. I always know where the closest bathroom is. That is awesome. You know, this is one of the most awesome thing about this version of the Dijkstra's algorithm is it doesn't give you just one shortest path, it gives you all the shortest paths from every vertex to a destination. Because you can now ask the question, oh, where do I go from C to a destination? Oh, you're right next to it. Where do I go from A to a destination? You got to go to C first and then to D. Where do I go to a destination? How do I get to a destination from B? Well, you got to go to D right away. Okay, that's the direct path. So that is the really kind of cool part of this Dijkstra's algorithm. So do we have any questions? So you apply the algorithm once, and you're guaranteed to find the shortest path from any vertex to a destination. So the only time you need to rerun it is when the distance functions got changed. Then you have to rerun it. So let's say, Six Flags decides, oh, we got construction going on, okay, so this edge here is no longer here. Then you have to rerun Dijkstra's algorithm because that can impact a lot of paths that you have found already. So are we good so far with Dijkstra's algorithm? So one thing you can do, it is not a homework assignment, is you can give yourself something like this, okay? Make it a little bit more complex if you want to. Throw a loop into it, okay? Throw a loop into the graph and see whether the Dijkstra's algorithm can be tricked by a loop and go like, oh, I'm getting into an infinite loop. But once you find out that the behavior of Dijkstra's algorithm, see if you can explain why it does not get stuck in an infinite loop. So even if your graph has a loop, Dijkstra's algorithm does not get tricked into the infinite loop and keep evaluating things over and over again. And that is the case even if your loop involves zero distance edges, which is really cool. Like you have a tight loop where the vertices are all connected by zero distance edges. You might think, well, since they're all zero, that means the Dijkstra's algorithm will keep going on. Nope, it does not. So you might want to find out which part of the algorithm makes it so that it does not get into an infinite loop, when you actually have a loop inside a graph. So that's kind of the informal, homework assignment for you guys to do before we meet again on Wednesday.